Okay, so hello everyone, and thank you organizers for the invitation. So I'm Christophe from CA, and I'm working on the development of a tool that is called Qbrix, and that aims at offering the possibility to perform formal verification of content programs. So I'm basically introducing some recent developments in Qbrix in this talk. Basically, the idea is that the field of content program verification has emerged and lived for maybe the last 10 or 15 years in a quite dynamic way. And it appears that a major challenge now is to lower the difficulty of using the tools that are provided by this field. In particular, I do believe very strongly in the strength of the past-time symbolic representation for this aim, and this is basically what I'm talking about today. And in addition, trying to show you some example of some recent developments in Qbrix using past-times. So I start with this consideration of the very simple schematic view and the so-called hybrid model. So there, the user of a so-called quantum computing machine actually doesn't address directly something that is quantum, but talks to a classical computer. And he builds a code that is a classical code with a classical control flow and so on. But sometimes it has a specific computing instruction that he delegates to the quantum coprocessor. The thing that is interesting for me in this scheme is that the user never directly addresses the quantum machine. And in some privileged scenario of usage, when at the time of building the code, of making the implementation, the user doesn't have access to anything that is quantum. And so there is a particular difficulty for programming. So it is the eternal question on how to get some assurance about what I'm doing. Is it right? Does it make sense does it physically make sense? And is it an actual computation of the calculus that I'm targeting? So in addition to this problem of having access to the quantum machine, if ever this guy had this access, then there would be in the act of verification and debugging a certain number of difficulties, of extra difficulties that are due to the nature of quantum computing. And it is quite an avenue, but we cannot rely on test assertion because of destructive measurement that would falsify the end of the execution. Final test is also hard to think about because what we want to verify concretely about a quantum algorithm is a distribution of probability. And so if we want to test it, we have to launch a number of tests big enough to rebuild a statistical distribution so as to compare it with the distribution of probability that is targeted. And so the short-term strategy so far has been to use classical simulation. That makes sense as far as someday there will be a quantum computer existing, and this is able to make some calculus that are out of reach for the classical computation, and this is where the real game is going to start. So yes, and with, in addition, the fact that it's not clear whether at time of implementation the user can really access the target quantum machine. So we believe in static analysis and the development of formal methods. So there, basically, we can talk about an engine, a classical program, that is able to look at the object quantum program, to analyze its structure, and from this inspection to infer the behavior of this program. Yes, this scheme. So, in the last decade or decade and a half, we have seen some efforts from a number of places in the world for the development of formal methods dedicated to the quantum case. Here I put, so this is a sequence of some selected publications in the field. I put many colors just to illustrate the fact that if we look here out of the major formal analysis method existing in the classical case, so type analysis, abstract interpretation, automata, proof, and so on. And it looks like the community has been exploring all of the main existing solutions in the classical case and trying to adapt it to the quantum case. And so, in every case, basically, you can say so, we end up with relevant proof of concepts. And especially when the formal verification of quantum programs is at stake, there are several propositions that proved able to implement, specify, and formally verify all the major standard literature from the quantum algorithms, at least in the FTQC case. So I think about Groover, phase estimation, Shor, and so on. So the conclusion of this period is that basically quantum formal verification exists and it is able to do things. Now, maybe a major difficulty is that even in the classical case, using the formal verification is something that is costful, and in many cases it is completely dissuasive for the user to be. And so, yes, in the general case, when it is about quantum computing, yes, we have the implementation of the algorithm. It is formally verified, but it is at price aside the actual implementation in any shape, a kind of side program that encodes the proof of the satisfaction of the specifications for this algorithm. And in the general case, this proof is big, it's larger than the code itself, and it requires a user or the developer to write this proof code. We need some extra expertise and dedicated expertise and a knowledge and maybe something affective also towards the activity of formal verification. And so yes, this can be a dissuasive point if we think about proposing the formal verification to, let's say, industrial users, or someone with a problem that comes from the real world, that never heard about formal verification, and who maybe doesn't really care about it. Okay, so this is the challenge to start introducing the solution I'm thinking about. Let's come back to the very beginning, to the algorithm that we think about implementing. So here is a screenshot of the phase estimation algorithm taken from the Nielsen-Schwang manual. First thing that I observed is that the procedure, the algorithm, includes as a full white part a big, or quite big, consistent preamble of specifications. So there are some input parameters that are declared. Here it talks about the size of the register, about the oracles, and so on. And within the algorithm, the specification function of this input parameters are given. And in particular, it provides some specifications for the correctness of the program. So basically, a success condition for run of the algorithm and the probability to succeed at each try. What is an interesting thing coming from that is that when we are implementing such an algorithm, what we are writing is a function that is to be run on a classical computer that takes as input some values for the parameters of the algorithm and that outputs a circuit. And the circuit itself is a computing object acting over quantum data. So there is a double level of computation, an algorithm, a function from inputs to circuits, and then a circuit computes over quantum data. One thing that I want to emphasize on here is the distinction between verifying a circuit and verifying a program. and a circuit being the output of a program and corresponding to one specific instance of the input parameter. So adequate validation or adequate verification when we are talking about a program should be the verification holding for any possible value of the input data. Now, when we come to the description of the procedure itself, so there is a kind of specific format of this description. It's quite light and it is double columned. So first we have some declarations for the instruction, the computing instruction to perform. So they are just declared here. And aside these commands, there are step by step description, a mathematical description of the state of the system along the performance of these operations, and a mathematical description of its evolution. So here it's taken from a book. So it's taken from a book. So do you want me to use the yeah?
No, maybe just remove your patch.
Yes. Okay. Yeah. Tell me if it. Okay. Okay. So yes, the command, the declaration of the instructions are accompanied by your description of the evolution of the state of the system. So here we are in a book, in something that is destined to a human reader. So the stake is just to facilitate the reading and the understanding of the algorithm. But we think about implementation and we think about verification, and so this can be also a reference for trying to find a format for writing our specification and for the verifications that we are looking for. So consider this. The the definitive goal for this seek of simplicity informal verification would be to be able to write the code in this kind of format by just declaring or defining or putting the main computing instruction and accompanying it with direct description of the state of the system in a format that would resemble as much as possible the format that real people are used to read and to manipulate. So it means that we assume or we take it for granted that we will have to input in the program some ghost material, so some information talking not about the operations to perform, but about the semantics. So we accept this as a prerequisite. And then the objective is triple. First, to describe the state in a format that is close as much as possible to the real-life description of state, and just mimicking this vectorial form. Then the objective is also to limit the ghost ingredient that we are going to input in the program to these intermediate descriptions. And then, of course, the far goal is to have a fully automated verification of this kind of specification. Okay, so the generic strategy from here is to integrate this kind of assertions in the object language, and then we have to design a verification engine. So I follow on with still the same picture. So this pink thing is just a zoom in from this part of this picture, and so this focuses on the format of representation of the state in these specifications. And just we observe that there are some patterns in this description. So each time the state is described as a sum of the vectorial terms, and each of the term is maybe a phase parameter together with a function pointing to the computational basis. And so we have this sum, and then it is normalized by a constant factor. And so the path sum symbolic representation that I talked about, basically, strictly speaking, is a formalization of this invariance. And it starts from the observation that for any state of the computational basis, for any unitary to apply, applying this unitary to this state results in a vector with this generic shape. And this generic shape consists in, again, a phase factor that is function of the input and the index of the path or of the vector term that we are in. Output function, again, function of the input and of the path we are in. That is basically a vector of binary function pointing to the computational basis, and a simple integer parameter that rules at the same time the constant normalization term for the whole sum, and also the range, the number of passes that composes the sum. So basically, there are how many sum terms as the number of possible assignments of R different path variables that are binaries. So it's, yeah, there are 2 to the R. Okay, so we have this format. Then we are just abstracting everything talking about vectorial complex states. So we don't mind about the sigma, about the complex exponential, and we just care so far about the parameters to enter in the path sum format. And so we are going to just manipulate these simple data types. And given this tuple, so an R, a PH, and a K, something green, something red, and something blue, we are able to analyze a circuit and to read its evolution. So just to exemplify, so the formalism interprets the elementary gates. In particular, so here is the Hadamard. The Hadamard supports the quantum superposition. So in the path sum, it adds it increments the range parameter, meaning that for every path in the original path, after the Hadamard, there are 2 different passes. So the same for the other elementary gates. Then there are functions interpreting compositions, either sequential or parallel, and we can indeed walk through a quantum circuit and derive directly, by applying this transformation, a path sum corresponding to this circuit. So this is a ground for symbolic execution, but yes. But it's not enough in the general case, because this gate-to-gate path sum analysis is not optimal. And basically, there are more path sums, we can see it this way. There are more path sums than unitary operators to analyze or to compute. And so maybe we don't end up with the best path sum and the best representation of the state we expected. So here is a simple example. It's a X gate surrounded by 2 Hadamard. So it's equivalent to a Z gate that just apply a phase transformation of -1. And with the gate-to-gate path sum analysis, because we meet 2 Hadamard gates, because an Hadamard gate adds an element in the range, increments the range, then we end up with two different path variables, which means a sum of 4 different terms. And so to manage or to deal with this effect, this equivalence or this extra information in the path sum formalism, it is provided, in addition, a rewriting theory. And here, I paste the main rule in this theory. So basically, I won't go into the details here, but basically, it is able to identify some patterns with destructive interference between the different passes, and to cancel out these passes that interfere destructively. And in particular, it enables, in the case that we saw, to come back to a simple path sum and the one that we could intuitively expect. So, as a conclusion about path sums, they are a compact, flexible, and intuitive symbolic execution format. There are also some good interesting meta-theory result. The calculus is complete and confluent for Clifford, and it is still complete, while not confluent, when we take a universal fragment of the calculus. So the Z star here means the Clifford plus arbitrary Z rotation gates. It has known great successes in the case when circuits were at stake for the problems of verification of specification and verification of equivalence. But if we think about, and we think about using them for the verification of programs as opposed to circuits, so with arbitrary sized registers in particular, then there are still some drawbacks in the formalism. And upon them, the format is quite restricting, which makes much sense when it is devoted to the treatment of circuits, but which is yes, less relevant for programs. Then the formalism also provides no means to analyze the measure, nor the quantum control, and of course it is non-parameterized. So using the toolbox for program verification will require some updates. Okay, so basically just lifting the gate-to-gate analysis from the instantiated to the parameterized case is quite straightforward. So since a program is a function from parameters to circuit, we can lift the passum analysis as functions from parameters to passums. But now the challenge or the difficulty comes when it's about the rewriting and simplification of passum writings. And here I distinguish between three different cases of affairs, three different kinds of rewriting of reasonings that we need for the analysis of programs. The first one is just about rewriting along the theory of the leaf types, the leaf data, the simple data types that are used into the passums. So here is an example of just an equality between two integer expressions. So we need to be provided some means for that. On the other extremity, at the highest level, we also need, by experience we saw, some means to reason in contexts where passums are taken as basic objects and to make some reasoning about their composition. So here is the switch between the sequence of two parallel composition into the parallel composition of two sequences. So this is a second pattern, and the third one corresponds to the rewriting in the sense of the passum theories. It is when the very structure of the passum is involved, and when there are some transformations that affect at the same time the different components of the passum tuple. And this is basically harder to proceed. A little aparté on the formal verification technique that I'm using. So it's called deductive verification. Basically, we can write some object language code and explicitly annotate it with some precondition, postcondition, and loop invariants, and so on. And I'm working embedded into a tool that is called while3, and that has the particularity and the advantage that when we compile this decorated code, so it raises some proof obligations to discharge. And to discharge these proof obligations, we can directly address a number of SMT solvers that will try to make the proof completely automated. And as an alternative, yes, it's not in the slide, but as an alternative, while3 also provides an access to a user interface where the user can enter some commands for the simplification of proof obligations. So there's two possibilities, either research automation or make the proof or input something to the proof to help the dischargement. So some demarcation criteria about that. Yes, it's quite intuitive. Basically, if the proof doesn't involve the introduction of extra parameters, then we have good chance to believe that they will be automatically discharged by the prover. And if we need to input some information to make the rewriting or the transformation, then it's more complicated. And so basically it fits more or less the distinction that is there. And when it is a rewriting of a pass-sum, generally it implies a factorization, and it needs to provide the proof a pattern. And when it is about algebraic reasoning about pass-sums or rewriting simple data types, then we have better chance to have the proof completely automatized. And so the strategy here is to take the best profit on SMT solvers and to let them in charge of all the proofs about algebraic reasoning and internal types reasoning. And for the last category, the rewriting, to explicitly command the rewriting from the object language. And so this rewriting rule will be full write instructions from the object language. Okay, so basically, maybe I'm going to be quick on that, but this is about the updating of the rewriting theory to the parameterized case. So here is the generalization of the HH rule as an application to an arbitrary sized register. So I called it the QFT rule, and it's quite cool, but I think I don't have time for going further on it. Also a generalization of a principle of substitution of variable that is present for circuit in the original theory as a substitution of one single variable, and then here it is updated as a substitution function for, again, an arbitrary sized register of pass variable. In addition to that, the pass-sum the pass-sum also provide tools, or naturally inspire some tools for reasoning out of the pure unitary case. And concretely, there is a continuity between the representation of an operator and the state. Basically, a state is just a constant operator, and there are also some tools to reason on the deletion of information. So here we have the parallel pass-sum composition scheme, and it also has a variable precondition for the separation of states over different registers, and enabling to define a discard operation about the object. We also have tools for formalizing the projection, so for the analysis of the quantum measurements. So basically, when a pass-sum ends up with the direct mention of some pass variable in a given subregister, then we can fix these values for this register and delete the sum over the corresponding pass variable. This enabled to treat the measurement result for the major FTQC algorithm that we meet in the literature. So far, I didn't meet any case where this projection scheme, together with the possibility to apply the variable register substitution, I didn't meet any case where it wasn't sufficient. Okay, so I end up with a quick show of the implementation experiments that I led recently. To do so, I just introduce a little bit of syntactic sugar. So here, the object, what we are programming, what we are building, is not just a circuit, but a couple of a circuit and its interpretation. So we have this couple of an instruction or a set of instructions and a PPS that is a parameterized pass-sum. And basically, the kind of specified assertion that I use is this one, where there is an initial state, and then there is a variable configuration, so a variable object of this type. And the idea is that we apply some configuration updates, and this function here, that is a syntactic sugar, ensures the fact that the satisfaction is preserved along the update. So which basically mimics a or assertion from the initial state. If my config is correct before, which means that the pass sum represents the execution, or the execution ends up with the pass sum, then it is also after my new instruction. And so we can use it as a primitive to implement the algorithms that we find in the literature. So here is, as an illustration, the CHOSA. So there is a preamble of declaration of parameters and the specifications of the algorithm, 2 consecutive definitions for the pass sum intermediate state that we are going to meet, and then we can make or write the computation just by using this update specified assertions that we meet before. So here is the circuit, and we find the different instructions corresponding to the blocks that are represented. So we place an Hadamard gate, then there is a composition of a parallel composition of Hadamard, the oracle, and again a column of Hadamard. Another illustration, so I didn't introduce the circuit, so I don't know what it really holds, but this one is a bit different because it involves, in addition to some purely computing instruction, some rewriting instructions, and they are there. So here we have the circuit itself, and then 2 different rewriting instructions, one occurrence of a variable or variable register substitution, and one occurrence of the QFT rule. And so the format is homogeneous. And the third example is, because it is the one that we saw in the picture, it is the quantum phase estimation. So here again, a preamble containing the general specifications, a little bit of intermediary definitions, and in particular, the intermediate pass sum description state definition, some definition for the instructions, and the core code formatted by this specified instruction function that I introduced. And there is also a post-process dealing with the analysis of the end state and deriving the specifications for the probabilities. Okay, this is the one. So as a conclusion, so if I come back to the code, to the goal, that was to make the code basically look like this as much as possible and to not require any extra input. I would say that I'm quite happy with this objective. First, about sticking to the vectorial nature format as far as possible. So here I think the pass sum is very powerful because it is really, strictly speaking, it is just let's say, natural or the common or the standard or the literature format for the description of states minus some elements. So it is exactly that, minus the sigma, minus the complex expansion, and so on. About the objective to limit the ghost ingredient to this, so globally, it's not far from that. I didn't insist on it, but the delta towards it mainly consists in the fact that there are iterators that are provided by the language, and applying the iterators needs to input a pass sum invariant. So this is the main delta. And about the objective of full automation, I would say I'm on the way to it, I hope so. So some of the algorithms or some of the experiments that I led could support full automation, like for the Fourier transform or the Dutch CHOSA. And I have a residue for the phase estimation. For the modular addition that we saw quickly, also there are a residue of human command to enter to finish the proof. So this is a count of how many times I had to enter some extra information in the proof. Yes, basically that's it. And yeah, further direction would be to extend the practice and the formalism to the hybrid case. And also, I'd like to tackle the consideration of less structured cases than the one that I talked about. Thank you.
Any questions?
Thanks, and thank you for your talk. I'm curious. I think that this is just like a clarification question. So how do you capture like algorithms that involve measurement, for example, or even going beyond like into hybrid classical quantum classical algorithms? Are those sort of expressible in this system in a scalable way? I just didn't quite understand.
Yeah, thank you for the question. I don't have the definitive answer to this question. Okay, but actually there are two levels of partial answer. How do I handle the measurement? So far, basically, I have this kind of partial solution, and I've been a bit quick on that. But you know, when you have a path sum, if you have the luck that at the end of the analysis, in your path sum, you have directly the expression of direct path variables, then you can just instantiate them, and you have the projection of your original path sum to the state that you expect. So this is quite restrictive, but we can rewrite, if we find the bijection, we can rewrite the variable, so it opens a bit the preconditions, and maybe I had luck so far, or it happened that these cases, this pattern or this tool unable to formalize and to analyze all the standard algorithms that I found so far. So yes, there is a question anywhere about where does it come from, and is there something complete? Can we always find the bijection, and at which price? Do we have a heuristic for finding it? And so far, yes, my answer is that I didn't go further into this question so far, and yes, going over just the using of this scheme, is a part of extra or further project, I would say.
Any other questions?
Thanks. On your last slide, you said one of the dreams was to handle less structured cases. What's the sort of structure you rely on at the moment? I didn't quite capture what this handling less structured cases means.
Are you asking me what I'm thinking about when mentioning less structured cases?
I'm asking what current structure you depend on, like what structure is being taken away in this sentence, I guess.
Sorry, again, I'm not sure to fully understand the question, but what is the advantage I take from structured cases so far? Or?
I'm asking what do the less structured cases look like?
Yes, I'm thinking of, basically, you know, I've been working with Groover, with Qp, with the Qft, and where there are lots of gates, but there is one or two loops or one or two iterators and so on. And I'm basically thinking about how this formalism would behave in a circuit where each instruction would be different. And so I like to see what happens for VQE, for example, and also if it makes sense, maybe something that has been post-processed at some points, and yes, resulting from a step of compilation, and what can we do, and if everything is not structured and with beautiful generic transversal boxes, what happens?
Okay, thank you.
That's it.